Right. So, hi everyone. I'm Olli Ruokojoki. I've been working at Cactos for 1.5 years now as a data scientist. So, I'm also a Cactos person. Meanwhile, I've been studying for my master's in engineering and physics at Aalto University, and I'm looking to graduate by the end of the year after completing my master's thesis here at Cactos. And today, I'll be talking to you about my master's thesis topic, which is data-driven batteries, modeling state of charge and state of health from operational data. I'll be focusing on the data used for the analysis, the complexities in the data pre-processing, the model itself, and the challenges that come from using operational data to build such an intricate model. So first, why do we need to estimate the state of charge, or SOC? The SOC is essential for battery operations. To make battery operations optimal, you need a really accurate and stable SOC estimate. So as you saw on Jussi's slide, this is the lowest component and everything is based on this. So if the SOC estimate is bad, and also the other stuff can't be optimized. This brings us to that if you have bad estimates, this can lead to unexpected SOC behavior, inefficient operation, decreased revenue, and even energy imbalance, which can result in hefty fines for the operator. The thing is, SOC can't be measured directly. It has to be inferred from operational and environmental parameters, such as voltage, current, and temperature. And in order to use these, a battery model is needed. So, how to create a state of charge model? The simplest way of estimating the state of charge is just integrating current over time, basically calculating the amount of charge that's going in and out of the battery. But the issue with this is that the estimate can drift over time, and it may be inaccurate because of the initial state of charge estimate might have been inaccurate. The second option is to estimate the state of charge with measured voltage. The idea behind this is that voltage grows monotonically over SOC, and thus you can always map a voltage value to a certain SOC. But the issue here is that under load, the voltage fluctuates by a lot, and to remove these fluctuations, it's essential to create a battery model. Of course, this can be combined using, for example, an extended Kalman filter, which combines the confidences of both approaches to create the best estimate. And in this presentation, I'll focus on the voltage measurement part because I'm talking to you about how to create the battery model needed to use the voltage measurements. Here on the right, you can see what the measured voltage values look like versus state of charge. It is very messy, so trying to estimate a state of charge from a single point on that plot is quite impossible. But keep this picture in mind because I'll show that to you later with all the fluctuations removed with the battery model. So, how to create a battery model to be able to use the measured voltage? The standard way is extensive laboratory testing. For this, one needs precise measurement equipment, controlled temperature chambers, as well as specific testing procedures that can last weeks or months or even years. This testing can be expensive and it's often not representative of real use case because the cells are in such a highly controlled environment. So at Cactos, we asked, what if we used operational data instead? That way, the model would be actually fit for the application and we wouldn't need any extra equipment. Here's what 7 days of operation looks like. There's the voltage, current, temperature, and as you can see, the data is quite chaotic. So trying to estimate state of charge from those curves themselves would be quite difficult. Also, creating an accurate model from this is quite difficult. And this also because some parameters require specific test sequences, which are quite hard to find in such data. Also, as there is no ground truth SOC, both model creation and validation are much more difficult. There's also a circular dependency in that to create an SOC model, you would have to have some SOC estimates already. Lastly, as this is quite novel, there are no examples in literature to do any of this. But as we'll see, it may be possible to create an even better performing model because it's built on the actual application. Now, getting into the actual model itself. Here on the right, you can see a picture of an equivalent circuit model, or an ECM. It is a very common way of simulating the voltage of the battery cell. These components drawn into it are normally characterized with the mentioned laboratory testing, but we get them from the data. And as you can see in the table below, it is from my master's thesis. All of these components depend on multiple parameters such as SOC, temperature, current rate, current sun, as well as aging of the cell. So extracting all of these individual dependencies is very difficult from operational data. But with an iterative model creation approach, I was able to find many of these. So briefly, the idea to overcome this circular dependency and observability issue is to start with at least some initial SOC estimates, for example, from the current integration approach. Then data pre-processing for later parameter extraction, for example, by finding specific test sections and stable sections in the data. Then fitting the parameters in a smart order in which the parameters can be observed individually without dependencies on each other. More on these in the next slides. Once we have some initial SOC estimates, we can pre-process the data to find specific test sections for parameter extraction. First up, time-dependent parameters. For these, I assume exponential decay of the voltage response, which creates the shapes you see here on the right. Actually, there is the orange line represents the simulated voltage across that section, and then the blue line is the measured voltage. And to find these sections to fit to, I look for steep, sharp current changes in the data, as well as a stable current prior and after the step. And using these sections, I can then find the time constants as well as the ratio between the fast and slow resistance components. The key idea here is that the resistance magnitude isn't known yet, but the shape is consistent, so that can be fitted first. Next, I want to find the resistance parameters and the dependencies. To simplify this process, I assume separable dependencies, which results in this equation. So the total resistance being a product of three parts: the current dependent resistance, an SOC dependence factor, and a temperature dependent factor. Again, before fitting, the data preprocessing is essential. For this, I focused on finding stable sections in which all the dynamics have fully evolved. And then I can calculate the resistance at these stable states and fit the current and temperature dependencies. Here on the right, you can see the resistance as a function of current, and there also the temperature as the color of the points. Clearly, there is a dependency in the resistance decreasing both with increasing current and increasing temperature. And lastly, after fitting the current and temperature, I then fit the SOC dependency using the residual resistance. And then this process is cycled until the parameters converge and that model is created. So, does this approach work? On the right, you can see the performance of the developed model. At the top is the current measurements, which fluctuates quite a lot. And in the center are the different voltage components, which all have different magnitudes and time constants. And then, most importantly, here in the bottom plot, you can see the simulated voltage as green and the measured voltage as the gray line. As you can see, these overlap extremely well, almost perfectly. So this indicates that the simulation is working and represents the actual self. So then across a lot more data, Here you can see the SOC model results across 67 sites, 44 years worth of data, and 55 gigabytes. Since this model was created on operational data, there is no ground truth SOC to compare to, so the SOC model must be validated indirectly. The goals for the model is both accuracy and stability. So for validation accuracy, I chose the voltage RMSE, so comparing the simulated and measured voltage. And then for stability, the cumulative Acton common filter innovation across all sites. On the right, you can see a histogram of the voltage RMSE values across all the sites. The median voltage is RMSE is only 7.65 millivolts, which is extremely low. Literature often reports over 10 millivolts RMSE or even tens of millivolts. Then below that, you can see all of this plot basically shows that the estimates are quite stable over time. If they weren't, then there would be a lot more fluctuations in that bottom plot. But why doesn't matter? First, the model is fit for our cells in real use. We also don't have to spend any time or money on laboratory testing, and the batteries can remain in use, generating revenue for Cactos and customers. Since the model was created on operational data, it represents our cells and adapts to real-world conditions. This enables further improvements through more data or advanced models, as well as analysis of parameter evolution over time and aging. And as promised, here is the after picture of what the voltage looks like after removing those dynamics. So there's the original RMSE picture, and then with the model, you can remove a lot of the fluctuations and see this beautiful curve shape. And then from this, extracting the SOC with a single point and voltage estimation is a lot more reliable. This brings us how the SOC model can be used to build a state of health model to track remaining charge capacity. The basis for creating this model is having an accurate SOC estimator and a framework for analysis like this. On the right, we again see the same curve shape with the points of the estimated voltage. And by looking at these across different sections, one can estimate the state of health, the remaining charge capacity in the cell. So key takeaways. Operational data can be better for creating models for real applications compared to laboratory data, but this does bring some challenges. For example, the need for an iterative approach to overcome circular dependencies and observability challenges. Through data science and domain expertise, you can create novel methods and accurate models from messy data. This does require quite a bit of work and creativity, but results speak for themselves. That's it. Thank you all. I hope you found this brief introduction to BTB and Butterfly. Yeah. When did your presentation start? It now or is there time for questions?
Interesting questions. So I'm sure we can have a few questions.
Go ahead. Yeah.
I have two questions. First, um, how actually in real life, from commercial perspective, do we want to, how accurately do we want to estimate state of charge of the battery? I bet we do not need 1 millionth of a percent. How much do we really need?
In the millivolts range, but it also depends on the application. So for us, it's really important to have accurate estimates so that in operations and optimizing them, you have confidence in the estimates and can bid more energy and create more revenue. But in, for example, some electric appliances, it's not as important. Millivolt range.
Millivolt, you say in case like how much in the percent? Assuming that the maximum voltage range of a cell is 3 point something, and then
Then talking about inverse.
Yeah, there you can see it's about 3.3 volts for, so 3,300 millivolts for an LFT cell.
And a second question, am I getting it correctly that your model does not depend on battery chemistry?
It does depend on the battery it was trained on, but the Yeah. For example, these curves changes a lot with battery chemistry, and LFP cells are extremely difficult in that the curve is very flat around the middle section. So estimating the SOC from voltage is very difficult. In different chemistries, it can be a lot easier.
So it will work, but will give less precision.
Yeah, and if you use the same chemistry, you can just change some parameters and it should work. And then when more data comes in, you can refine that model for the specific cell. And there in the back.
Yeah, great talk. You said it depends on the battery like chemistry, but does it depend on the individual battery? My question in general is like, how many models have you trained? One for all of your fleet or one per battery?
It depends somewhat, but the general trends are the same across different cells of the same chemistry. So, well, for example, here you can see some of the like current dependency and temperature dependency. The shapes are the same, so or the trends. So this can be used for others, but it can be refined for the specific cell. Also, there's an example of an NMC cell, so the curve is much more linear, so easier to use. Yeah, go ahead.
So yeah, great talk. Wondering about this flat part that are you then mitigating that by estimating the load or something that that goes out of the battery with
Yeah, that's the current integration, so Coulomb counting. So in those sections, the extended Kalman filter doesn't trust the voltage measurements, but uses the charged integration.
Okay, is that
Yeah. Or I didn't focus on that.
very nice.
Thank you all.